Hello, everyone. Welcome to our webinar today. Um, it, I think it is the fourth one of this series webinar. Today, we will focus on how to use some tools in WinSim to check the quality of your safety model. Yeah, basically, from the last webinar, we were discussing how to use different safety settings to make your safety model could be handled in a correct way. And today, when we set up the safety model and run safety simulation on accelerator or on your local machine, and now it's time to check the quality of your safety model. Of course, I think we could skip this. We have almost the exact same attendees for the series of the project. That's me. That's me. Anyway, you guys can access me through my email. And then today's agenda will include almost the same introduction, common mistakes and pitfalls, and two tools in WinSim we will look into for today. That is, one is cross-checking. The second one is flow model validator. I think cross-checking is quite easy to be found in WinSim, but flow model validator is a little bit harder for some of our customers to find and to use. So maybe today I will spend some time and show you guys how to use flow model and how to use flow model to give you some suggestion on how modify your safety model. And then we will follow by best practice summary, and also we have a QA section. Of course, who should attend this kind of webinar? Of course, project engineers who operate WinSim, because this series of the webinar will focus on operation of WinSim always. And today's objective is I would like to help you guys learn how to use tools in WinSim to check the quality of your safety model. Yeah, here I listed some common mistakes or pitfalls that could be quite common for some of our customers. The first is some of our customers simply use the neutral simulation results for WRG and AEP. Basically, they set up the safety model for neutral case only, and then they don't check the quality. They don't check the safety model quality at all. Just use what they got to calculate the WRG, to do the post-processing and calculate the AEP. That's very common mistake or pitfalls I used to see. And second one is simply do cross-checking. These customers, they will do cross-checking, but they just check the overall values of those error, of those cross-checking results, but they will not further check by sectors. And of course, most of them will not modify safety model at all based on the cross-checking results. And then some of them may understand how to use flow model validator, but don't know how to modify safety model based on it. Actually, both cross-checking tools and flow model validator tools could help us to improve the safety model and make it more accurate. Today, we will focus on cross-checking and flow model validator. So I think some of you guys are quite good at WinSim, and some of you may be quite familiar with these kind of tools already. So I will try my best to explain further and expound how I think about these kind of tools. Okay, the first thing I would like to say is when we start to check the quality of your CFD model, there are also some prerequisites. Because when we start to check the CFD model, especially when we use these tools to check that, we might need to make sure that our CFD model from the very beginning is a good one, including we use the good elevation and roughness data set. Actually, I'm not quite sure about this because some of our customers simply use some data set of the elevation in global mapper, for example, SRTM, even for dense forest area. But actually, maybe you guys know that SRTM database or dataset was some satellite image was obtained from some satellite image, and they cannot remove the height of the forest or buildings. So if you use SRTM elevation dataset to build wind farm project in forest area, basically you will place your turbine on the forest. That also means if you use this kind of elevation data, you will overestimate the AEP value. That's something we need to keep in mind. But for some area like bare land or some other without or very less forest area, then SRTM still could be used very efficiently. And for those area with dense forest, I would like to suggest to use so-called FABDM database. That's one thing I would like to say. And then good CFD model settings. That's something we have covered in the last webinar, and also some webinars covered by my colleagues. And then we should also have very good convergence. Some of our customers, they don't, they use accelerator and they could check the convergence and see whether it's convergent or not, but they don't know how to check how close. For example, you set the convergence criteria to be 0.0005, and how close when the iteration of the CFD simulation ends, how close the residual, or how close the residual has reached, or what's the difference between the residual and the convergence criteria. You could use, actually, you could use accelerator to check that. Maybe later I could show you guys. And then we also need good measurements, because when we check the quality of CFD model, we rely on the measurements. We believe that the measurements are good. Otherwise, if we use a wrong standard to qualify our CFD model, then everything will be wrong. Actually, for this, I would like to point out that sometimes we often talk about whether the measurement from the MetMask or from the LiDAR could represent the site well. But actually, it's a big problem. I have to say, it's a big problem. For example, this is a very complex terrain. You can see the picture here, and I'm not quite sure whether you guys could see the yellow curtain here. It's the location of the MetaMask. It's the location of the MetaMask. The customer asked us to use this turbine, use this MetaMask to calculate the AEP while they place the turbines in front of the on the top of the hill here. And the difference on height between the measurements and the top of the mountain is like 400 meters. And when you run CFD model, you will see the speed ups between the locations of turbine along the top of the mountain, and this measurement location is about 1.3, 1.4. This level. That basically means this MetaMask cannot represent those turbine locations. So by using the speed up you obtained from CFD model, you could evaluate whether this turbine, this MetaMask could represent the site well. That's something I would like to say. So maybe it is possible for you guys to also keep this in mind that before we run any CFD model, we need to check whether this MetaMask, the MetaMask could represent this site. The speed up between the MetaMask and the potential turbine location should be in a range like 0.8 to 1.2. If it is go up to 1.3, 1.4, then it doesn't make any sense to use this MetaMask to calculate the AP for that wind farm. By the way, we also provide this kind of consulting service to pick up the proper location for your MetaMask or LiDAR to measure the wind condition in some area in the area. Yeah. And then we move to the first tool we would like to introduce. That is cross-checking tool in WinSim. Basically, in WinSim, we use one or two or multiple MetaMask or measurements we call climatology to use the speed up obtained from CFD model to extrapolate the wind speed to any location in the wind fields. So this kind of speed up is extremely important. And in WinSim, basically, if you have multiple climatology or multiple MetaMask data or measurement data, we basically use one MetaMask or one measurement as the reference, and to use CFD model by speed ups to calculate the wind speed at other MetaMask location or other climatology location, so as that we could compare the results from the CFD model and from the real measurement, and get the error, obtain the error between the measurement and also from results from the CFD model. And I think you guys should be very familiar with this. Is in the wind resources module. In the wind resources module, if you turn this wind speed cross-checking and turn this into true, basically you open the option to export the cross-checking results. You will see here, there's a table which shows from, for example, from one MetaMask, you use one MetaMask as reference and then use CFD model to get the results for another MetaMask location. For example, here the reference, here measurement, reference wind speed is this value, and the target measurement is this value, while this target model is what we obtained from CFD model based on the reference measured value. And then we could find the error here. Basically, we use this kind of value to evaluate the quality of your CFD model. Because theoretically, this kind of location of the reference measurement and the target measurement, or both MetaMask, is kind of random. So we believe that if we transfer from one MetaMask to the other locations, the error should be quite similar. But of course, it is also rely on the distance between those locations. And then if we find the error is small, we are very happy. And for example, for this one, we see the error is less than 1%. We are very happy. And of course, there are some rules I would like to point out as well. For example, when we should do the cross-checking. My suggestion will be we should always do cross-checking if you have multiple measurements available. But some of you may be argue because theoretically, only when we have concurrent measurement data, we could do this kind of cross-checking. But if we don't have concurrent measurement data, how we could do that? Yeah, I still suggest that we do this kind of cross-checking and check the average wind speed. Check the average wind speed for different years. Because although it was not in the same period of time, but the average wind speed still makes sense. But of course, we need to check further about the yearly variant. Those data we could study from either mesoscale data or reanalysis data. That's something we still could study, and we could still compare. And then the second one is how. Yeah, that's the second thing I would to emphasize, that we should always use wind speed at same height, usually at half height, because we will see later, because for CFD models, the vertical profile could be a big issue for most of the simulation. So we usually use some third-party tools like a windographer to extrapolate the wind speed to the half height or to the same height where we have the measurement, and do the cross-checking at that height. We will not run cross-checking in WinSim from different height. It was proven that for CFD models, to do the horizontal extrapolation is kind of more accurate than doing the vertical extrapolation. That's the reason we always use the wind speed as the same height to do the cross-checking. And the third one I would like to say is accept whether what kind of error we should accept or when we should modify based on the error. According to my experience, the overall error should be like 1% per kilometer. We need to check the distance between the mast. For example, if the distance between the mast is like 4 kilometers, then the cross-checking error, overall cross-checking error, should be less than 4%. Less than 4%. And basically, when we submit this kind of result, it will be accepted by the third-party audit. But like what I said, we should not only check the overall errors. Sometimes we also need to check each sectors. We should check the errors from each sectors. For example, here we could see the largest error was from the sector 2. The error is like 5.08%. Then we got some idea how those error from different sectors and what's the contribution from each sector. And then we could get some idea if we would like to improve the quality of our safety model, which sector we should focus. Then for this one, but of course, this one is one index, and the other one is the frequency or we should focus on the prevailing wind direction, prevailing sectors. That's the second important thing I would like to say. Focus on those sectors with the biggest errors and focus on the prevailing wind directions. And then we move to the fourth question: how to modify? Like what I have shown, we need to check further for the error of each sectors. And we focus on the sectors with large errors and in prevailing directions. And then we check with flow model validator. Because most likely, if we got the big error, that basically means for that sector, we may need to change some safety settings. So how to validate the safety model at that specific sector? We need to use flow model validation. And then for flow model validator, I'm not quite sure. Maybe some of you have some experience to use that, but maybe some of you maybe have no idea what it is. Flow model validation is a tool in WinSim. You could find in tools here, flow model validator. And if you click on this, an Excel sheet will be opened. And then the first page is description page. If you don't know how to run flow model validator step by step, you could use this as a reference and run it step by step. simply you need to run terrain module, wind fields module. That's something you need to run first, and then move to objects module. In objects module, you need to input climatology or metamass data at least two, actually, at least two. And then you need to keep this in mind. If you would like to run flow model validator, you need to at least have one turbine in this model. It actually is not necessary, but it has been defined in WinSim flow model validator. You need to have one turbine inside the model. Otherwise, you will not be able to run it. And run objects module, you could then finish, when you finished running objects module, you could move to wind resources module. And you could keep everything as default, just start to run wind resources module. And you even don't need to change the height, just run. It will generate some file which was used for flow validator, flow model validator. And then we could also, we would need also to export vertical profile. You also need to use this tool to export the vertical profile from the CFD model at all climatology locations, climatology positions. Basically, here you need to run. You need to choose two. You need to choose two. And then after that, if everything runs correctly, you should be able to run flow validator, flow model validator, and input. Let's see. I will load one model here. Users. Project. This one. Yeah, you need to find the model file from WinSim project folder in layout report. This one. And after you input the model, you need to input the measurement data. Yeah, use this one and click load data. Then you will generate the vertical profile that include both vertical files from CFD model and also from the measurement data. The measurement data are dots, while the CFD model results are curves. So basically, you could switch different reference speed height. Like here, you could switch different height, and then you could check. This is results for all sectors. And here you could see from different sectors, the results could be different. Some of them could match the CFD model very well. The measurement could match the CFD model very well. But some of them may be not so good, maybe not so good. I also need to emphasize that, frankly, this flow model validator sometimes maybe not that stable, maybe not that stable. If you find there's some error, if there's some error which prevent you to use this flow model validator correctly, you need to clean you need to clean your climatology folder in your project directory. That is something here. I mean, this folder should only have the climatology files for this flow model validator. I have some experience. If I input too many measurement data here, then the flow model validator will not work. So if you cannot make the flow model validator work, you just clean this and generate one climatology folder that include only the climatology files that you would like to include in this kind of comparison. Okay, and then this is one example I have done as a consulting project. I got lucky, I have to say, I got lucky. And then for the neutral case, because I always use the neutral case as the baseline, and then to use flow validator to compare the neutral case with the measurement first. You can see for this one, for this specific project, the CFD model and the measurement data could match very well, very well. But sometimes it could not happen always. This is another example. You can see most of the sectors could not match the measurement data, could not, especially you can see here for the last sector. And from this, how we could use this kind of result? How we can use this kind of result to make some suggestion or to change the safety model, here I have two scenario that is quite typical from my experience. The first scenario is a safety model. Of course, this kind of safety curve, since it's just speed up, it could move here or move to attach one measurement height, to match one measurement height. And basically, I will always use the hub height to make the safety model result to match the hub height measurement. And then we can see that for lower height, the wind speed is smaller than the safety results, while for higher height, the wind speed could be higher or could be larger than the safety results. For this kind of simulation results, basically means we need to check. First, we need to check the roughness. Once again, I need to emphasize that for this kind of checking, we should focus on sectors, while we should not modify all sectors. We will not work on all sectors, but focus on some specific sectors, like with the largest error or smaller error, but the error, but in the prevailing wind direction. And when we see such kind of vertical profile, that basically means we need to first check the roughness, increase it if the roughness was said to be too small. And then we could also check the HBO if it is too high and see if it is too high. We could reduce it. If we find that the roughness and HBO is kind of good enough already, then we need to check morning up length from some other resources. Like if you have access to mesoscale data, you could check whether in this one direction, you could do some statistical work and check whether in this one direction, if it is stable condition, dominant. If it is, then we may change the morning buff length and run stable simulation for this case. But the most important thing is how, from this kind of profile, how we would like to determine which morning cutoff length is appropriate for this kind of simulation. That's the common question, or common question has been asked by our customers. It's frankly, it's really hard. It's really hard. Even if you have access to the mesoscale data for long period of mesoscale data, you could do some statistical calculation. You get the morning cutoff length. If you input that into the CFD simulation, the results could still be not that good. So practically, sometimes I often use a range of the morning up length, but use low resolution cells to compare when we change the morning up length. What's the difference between this kind of vertical profile? Because if you do more practice, you will find even for a low resolution, the trend of the vertical profile at the different morning cutoff lengths could be quite similar. That's something we could utilize. And then the second typical scenario is CFD model could underestimate wind speed at a lower height. Then we could do in the reversing direction. We check the roughness, decrease it if the roughness was set to be too large, or we check the HBO. If it is too low, we increase it. And we could also check morning length. If the unstable condition is dominant, we could turn to unstable runs or MMC if it is possible, because U runs NMC basically will will spend a lot of time. It will cost a lot, not only time but also the computational resources. And for WinSim customers, U-runs is maybe not possible yet, but for us, it is possible. For consulting service, it is possible. And MMC is also possible for consulting service, but yeah, we also provide MMC tools that could only be used as a coupling boundary condition in WinSim desktop version. And right now we are working to integrate MMC function into accelerator now. I think it will still take some time to make it happen. But of course, some of you guys may be not quite sure about, for example, what is the right roughness, what is the HBO. then basically it also rely on your experience. And right now, but at least right now we have some good tools to check the HBL already. Because I was not realized that AI agent was developed so fast. And right now it is possible to use OpenClaw to check the HBO values if you have a large database to support you in the backend. For example, here, since I have a large database to support me now, for example, I have the Canopy height database. I have HBO database in China and a leaf area index database, and also I have local SRTM DM database and FABDM database. I could use this kind of data to ask AI agent different questions and even ask it, I maybe not say it, but him. For example, if I would like to see the HBL at a certain location, I could ask him directly. What is HBL? For example, the location here. It will take a while. It will take a while, but that's something. That's something I have developed as a skill set. As a skill set, I could ask AI to help me to do different things. For example, here I ask him what's the HBL at a certain location, then it to give me a report that includes 20 years average data, and then for each month, what is the typical HBO height of boundary layer? What's the highest and what's the lowest? It could give us this kind of report. So yeah, I think this is something I cannot imagine even 1 month ago. But right now, I think everything becomes possible, and I think I would like to also update this kind of webinar based on what I have learned from AI recently. So yeah, we could conclude for today's webinar, and the best practice for checking the quality of your safety model is something you should do. Yeah, cross-checking the results for sectors rather than for overall only. You could see a better overall results, but if you look into different sectors, the results maybe not that good. Maybe not that good. You need to figure out how to improve the safety model for each sector. And then you also need to use flow model validator to check if the vertical profile at the climatology location could match the safety model. If not, then you could modify roughness, HBL, and monopic length based on the results from the flow model validator. Yeah, that's basically the idea or something I would like to share for today's webinar. And then I have to say that the next webinar, we will focus on how to extract the results you need from WinSim. But I think it was arranged, it was booked in May. I don't remember exact date, but I got the information that that date was a public holiday in Germany, so maybe we need to postpone it. and we will send out the notification in advance when we will have the next webinar. Thank you, guys.
Thanks a lot, Sven. So I think, do you think we should do a couple of questions, or should we?
Do we have any questions here?
Yeah, we have a few in the, let me see, in the Q&A tool. So we can do a few, and then we'll sum up the other ones and put it in the follow-up email. So I will try to do some of the shorter ones maybe. So I can start with this one. So how is the total cross-checking error calculated, and how is the sector-wise cross-checking error averaged?
If you click into these cross-checking tables, you will see the cross-checking error for each different sectors, right? And then there are some cross-checking files. You click on these kind of files. So for each time step, you can see for each time step, the reference wind speed was transferred into the target location by using speed ups between each other. And then you got this kind of long file for each time step. Based on this kind of time step, you could do the average for the errors of each. You could do the statistical calculation for different sectors and for different. This is yeah, for different sectors and for different targets, from the same reference. Yeah, you need to check this kind of file to get to those details. This is so-called time series error. Based on this time series files, you could do the average and do the statistical calculation. Yeah, basically that's it.
Thank you, Sven. So we'll do one more. So I think we can take this top one. So how can the roughness be modified only for specific sectors where it's needed?
Yeah, because you will only run that sector. So you just modify the roughness and generate a GWS file for that sector only. Because like what I said, different roughness and different HBO could represent different season, different time. And you could run that, you could prepare one GWS file specifically for that roughness for that sector, and run that sector only, and combine the simulation results with the previous results into the same project. I think you guys know those results, those safety results were saving in the WindSim project in the wind fields module. Just copy the results from that special sector and replace those results here, and then you will get combined results. Yeah, that's the way you do, you do the, some sectors could be stable, some sectors could have different HBO and roughness.
Thank you, Sven. So I see now we are a bit past the time. So I think we'll say thank you there. You have some final words, Sven? And
Yeah. Thank you guys. Thank you guys. And I think today I didn't present this well, but I think I do show what I thought here. Yeah. Thank you. Thank you guys.
Thanks a lot, Juan. Okay, thanks everyone for joining. See you at the next webinar.
Yeah. Bye bye.